Our next speaker is Professor Haiyan Gao from Duke University and Duke Kunshan University, and she's going to speak to us about proton, a fascinating relativistic many-body system remains puzzling.
Okay, so what I would like to do here is to share with you a few stories about proton. And this is a very fascinating relativistic many-body system. And the story I would like to share with you is about the proton charge radius, the spin, and if I have time, I will also tell you a little bit about how we can use proton as a laboratory to test and model and look for new physics. Now, nuclear physics, as we know, it is about study of the structure of matter. And most of the mass and energy in the universe around us comes from nuclei and nuclear reactions. And it is also very fascinating about nucleus in the sense that all fundamental forces are present in the system: strong interaction, electromagnetic interaction, weak, and of course, gravity. Now, at the heart of nucleus is nucleons, namely protons and the neutrons. And the length scale we're talking about is a Fermi, which is 10 to minus 15 meters. Now, proton, if you look at the proton, the simplest picture you come to your mind are 3 quarks, 1 down quark and 2 up quarks. But if you look more closely to proton, you realize it's a lot more complicated than this simple picture. And we were all very excited by the great discovery of Higgs particle at CERN. On the other hand, when you look at the proton mass, you might be disappointed in the sense that it actually, the mass from the quark, for example, the 3 valence quark contribution to the proton mass is only a few percent. And we also know that quantum chromodynamics is a beautiful theory of strong interaction. But on the other hand, at this moment, we still do not really know how we can start from quantum chromodynamics, QCD, to describe the proton and the neutron. So therefore, the study of the proton remains a very important laboratory for us really to understand how QCD works. So what is inside proton and neutron? And this quest has been going on for many decades. So let's take a look at the past accomplishment. In fact, the discovery of proton anomalous magnetic moment already tells us that proton is not a point-like particle. It has structure. And physicists started in the 60s or early in the 50s to use electron scattering to look at electron-proton elastic scattering in order to find out how the charge or current is distributed by measuring the so-called form factors. And the Nobel Prize was given in the 60s for such measurement. And you can continue to do electron scattering by looking deep inside the proton. And what you find in this case is the virtual photon will couple to point-like particles, which at the time were called partons. And these are the quarks we know, and Nobel Prize was given for this great discovery using so-called deep inelastic scattering. And to complete the story, and we also know that the discovery of asymptotic freedom was awarded Nobel Prize in early 2000. So the way to understand the structure experimentally, the powerful probe is lepton scattering. And this is the way I like to tell students, mostly at Duke. We have a lot of pre-med students, so they are very familiar with microscope. So what we're doing is also a microscope, except our resolution is enormously powerful. We are looking at 10 to minus 15 meter or smaller. And this is a very clean probe, which allows us to study hadronic structure, because we know the leptonic vertex very well from QED. So here I show you what will happen if you do electron-proton scattering. The first thing happened, horizontal axis is the energy transfer to the system, is elastic scattering. So that is Hofstadter's experiment, which got Nobel Prize. And the cross-section can be described in a very simple form by kinematic quantities for elastic scattering, as well as two form factors, electric and magnetic. And this has to do with the fact that proton is a spin 1/2 object. Okay, so if you give a little bit more energy, what happened? You excite a proton to make delta, which is the first excited state of proton. And you keep going on. Eventually, the virtual photon will couple, as I said earlier, to the quark inside. And this is so-called deep elastic scattering. And you can repeat the same exercise with atomic nuclei. So elastic scattering experiment, as I said, started many decades ago. And in more recent times, and the field has benefited enormously by the advancement in technology, such as very high intensity and duty factor electron beam, high quality, parity-violating quality electron beam, and larger substance detectors, as well as state-of-the-art polarimetry and polarized target. So the first important discovery in the field has to do with using so-called recall proton polarimetry by measuring the recall proton polarization using unpolarized proton target and longitudinally polarized electron beam. And what we have discovered is that when you go to higher momentum transfer region, which corresponding to smaller length scale, and the form factor ratio normalized by the magnetic moment of the proton is no longer as we think, as we used to think, which is essentially like 1. In fact, it has this dramatic change as you go to smaller and smaller distance. And so this is the situation at higher momentum transfer, lower scale. So what happened if I go to lower momentum transfer, which is larger scale? And here I would like to tell you about the proton charge radius. So if you do electron-proton elastic scattering, you measure so-called electric form factor, all the way down to momentum transfer equals 0 or close to 0. You actually can determine so-called proton charge radius. And why this quantity is important? It is important because, as I said, we really need to know how QCD works. It is also important to our atomic colleague because they are doing precision spectroscopy measurement and to compare with our state-of-the-art QED calculation. And for example, in the case of muonic hydrogen lamp shift, and the proton charge radius can contribute to the energy shift by as much as 2%. And this is important. And about 5 years ago, or close to 5 years ago, at CERN, at PSI in Switzerland, a new result was reported from muonic hydrogen lamp shift measurement, which caused a major excitement in the field. And what about this experiment? So the experiment involved muonic hydrogen, which is actually very difficult, as you may imagine, but nevertheless, people or physicists were successful in doing such experiment. So imagine you take muon beam and you actually excite hydrogen gas, and you can produce muonic hydrogen in an excited state and equal 14 state. And that will decay to, with 1% probability roughly, to the metastable 2s state. And then you can do spectroscopy measurement by driving the transition, which I show here as the green line, between the 2s1/2 and 2p3/2 state. And based on QED, you know the 2p3/2 and 2p1/2 state. So essentially, you are doing lamp shift measurement in muonic hydrogen atoms. As I mentioned that the sensitivity to proton charge radius is as big as 2%. So this allows you to do very precise measurement. Indeed, and this is the precision of the measurement of the proton charge radius. So this is really wonderful. However, it caused a major excitement because this value determined by spectroscopy is different from what we knew at the time from elastic electron-proton scattering as well as conventional lamp shift measurement from hydrogen. I should say lamp shift measurement from conventional hydrogen. And so the PSI collaboration, they went back and not only they reanalyzed the data, but they also provided a result from a different translation, which corresponding to the 2s 1/2 f equals 0 to the 2p3 half f equal 1 state. And also the result they published in 2013 in Science paper is consistent with their 2010 Nature paper and with even better precision. So here's the summary of the saturation. So you have the two high precision, so precise you don't see the arrow bar here from muonic hydrogen measurement. And here you see the cold data compilation based on world data as well as just looking at the conventional hydrogen lamp shift measurement. And here you have the most recent electron scattering experiment from Mainz in Germany using cross-section measurement and reanalysis of world data, including new polarization data from Jefferson Lab in US. So what you see is clearly a difference between the result from muonic hydrogen as well as electronic hydrogen or proton system. And the difference is between around 7 sigma. So what's happening? So the first thing you ask yourself is, what about QED calculation? Because muonic lamp shift measurement, you do a very precise precision spectroscopy measurement, then you have to rely on QED calculation to indirectly determine the proton charge radius. So physicists have checked QED calculation very, very carefully, many times by different people, as well as asking the question, what about certain effect you probably have not included or not looked at carefully, such as the polarizability of the proton. But not enough to explain this difference, which is 0.31 millielectron volt. And for atomic physics measurement, that's enormous. So what else? A lot of papers have been written trying to understand this difference, which involve new physics, new particle, new force, and quantum gravity, which you have heard in the previous talk, as well as checking everything you can imagine or any effect which has not been included, and people have looked at that. And of course, there are also papers written which explain that they can actually understand this difference, discrepancy, but not everybody agree. So as an experimentalist, it is important to go back really to look at the experimental saturation. And the good news is a number of efforts worldwide are trying to address this and mostly are focusing on the electronic hydrogen or proton system, like EP elastic measurement and also muon proton scattering experiment, as well as revisit the conventional hydrogen lamp shift measurement. So here I want to highlight one experiment which is under preparation at Jefferson Lab. And here there are a few important features. One is, as I mentioned, in order to determine proton charge radius, you really have to do EP elastic scattering near 0 degree measurement. And that is physically very, very difficult because all these experiments previously have used magnetic spectrometers. So this new experiment will use a calorimeter, high resolution calorimeter, which will allow the beamline to go through the center of the detector. So allow you to access very forward angle. And it also, in order to suppress the background, it will use a windowless hydrogen gas flow target, and also will simultaneously detect the molar scatter electron as well as electron-proton scattering. So we are working very hard in order to start this experiment. Okay, so this is the saturation with the proton charge radius. And let me switch to tell you the next story about the proton spin. Here is a compilation with some modification by my collaborator about the important milestones related to spin. As physicists, we all know the importance of spin in our field. And here I'd like to highlight a few important applications. One is nuclear magnetic resonance imaging functional magnetic resonance image. And all these applications use proton spin, or the magnetic moment of the proton. And on the other hand, you might be disappointed in the sense that we as nuclear physicists, we still don't really know extremely well where the proton spin comes from. And that's why in late 1980s, the result from European Muon Collaboration doing deep elastic polarized scattering, and the result came as a shock, and we have a name at the time called proton spin crisis. And part of the reason for that is because of the success of quark model. And we all know in our introductory particle physics book, and you can use 3 quark, 2U quark, 1D quark, and 2D quark, 1U quark to calculate the proton magnetic moment and neutron magnetic moment, and you even get the ratio right, and everybody was very happy. And so therefore, naively, you just assume the proton spin should also come from the spin of the quark, until the experiment from EMC, which tells us that very little contribution is actually from the quark. And that came as a big surprise, which motivated more than 2 decades of experimental effort, which still continue on. And this is a worldwide effort by doing all different kind of experiments using lepton beam, inclusive spin-dependent deep elastic scattering, and also semi-inclusive measurement, in which, in addition to detect the scattered lepton, you also detect the leading hadron in coincidence. And also more recently, polarized proton-proton collision at relativistic heavy ion lab at BNL, and also polarized electron-positron collision experiment at Bell and also Baba. Okay, so important accomplishment in the last few years in the business of proton spin really came from the RIC spin program, where for the first time, one sees the contribution of the gluon spin contribution to the proton. And this is actually a very important accomplishment in the field. So let me just show you where things are in terms of the proton spin. And we know that the proton spin is 1/2. And after more than 2 decades of experimental work, we now have very good knowledge about the contribution of the quark to the proton spin, which is about 30%. And more recent result from polarized proton-proton scattering now give us about 20%. Of course, that measurement is continued to be refined to cover more kinematics, as well as to improve the precision of the measurement. So that is still not enough to make the total proton spin 1/2. So what's left, remaining contribution is from the quark or gluon orbital motion. So then the question is how we actually access quantitatively in order to determine so that we can make the proton spin story complete. So let me just graphically to show you how we may approach this. And I talk about the quark spin contribution, and sometimes we call helicity contribution of the quark, by looking at so-called longitudinal spin structure function. So here is a picture. So imagine the virtual photon 3 momentum direction is labeled by this red arrow, and this big fat arrow representing the proton spin direction, or you polarize the proton spin in this way. And longitudinal spin structure function tells us the probability for quark to be polarized along the same direction as the proton spin. On the other hand, its counterpart we call transversity, which tells us about transverse spin structure, is the only thing you want to do is to rotate the proton spin in this case from longitudinal, which is along the virtual photon momentum direction, to perpendicular to that. Now, in the absence of relativity, these two should be the same, but we know, as suggested in the title of my talk, proton is highly relativistic, so therefore these two are not the same. So what we really wanted to look at the proton structure is to go beyond the Nobel Prize winning experiment the one-dimensional, the inclusive deep inelastic scattering, in which you only look at the momentum fraction of the parton inside along the virtual photon momentum direction. So we need to go beyond that to include the two-dimensional transverse momentum of the parton to bring those 2 degrees of freedom into the picture. And this kind of quantity are called transverse momentum dependent parton distribution functions. And I apologize, this slide is busy, but let me try to walk you step by step. So we talk about the form factors, and I just mentioned about parton distribution function, and which are the probability to find the parton with certain momentum fraction along the longitudinal direction, which is the virtual photon direction. And what we really like is to have a complete picture of the proton in terms of, we wanted to map the proton structure in 3 dimensions, and the tool or the framework we're going to look at is in terms of Wigner distribution, which is a 5-dimensional distribution. And so one of the way to look at this is if I integrate over the transverse momentum. So these 5 dimensions are the longitudinal momentum fraction, transverse momentum, and 2-dimensional transverse space. If I integrate over the transverse momentum, what I will left with is a 3-dimensional distribution involving 1-dimensional momentum along the longitudinal direction and 2-dimensional transverse space. That's called generalized parton distribution. And you can continue to do integration that will connect to the 1-dimensional parton distribution as well as the form factors by doing the integration over X as well as Fourier transformation. And likewise, if you integrate over the transverse space, you have the transverse momentum distribution. And if you integrate over the transverse momentum, you will get 1-dimensional parton distribution. So this kind of picture provides 3-dimensional imaging of the nucleon. And this is a major effort worldwide trying to access transverse momentum dependent distribution functions involving different kind of process at different laboratories. And a lot of progress has been made in the last decade or so, mostly from experimental side as well as major progress in theoretical phenomenology side. And currently, the 12 GeV energy upgrade at Jefferson Lab, which is the most powerful electron accelerator lab in the world, is about to be completed. And the 3-dimensional imaging of the nucleon is going to be a very important part of the program there. So just very quickly to give you a couple examples, what will come out of the future experiment. And I talk about the transversity, and if you do calculate its Searles moment, that gives us tensor charge of the proton, which is a fundamental quantity. And here shows the current knowledge with a model-dependent uncertainty based on the world data, global analysis, and together with different kind of predictions, including lattice QED predictions. And here shows that with 12 GeV measurement, you will have a high precision measurement and many, many bins in comparison with the current published data, just taking one slice as a comparison. And that, in the end, will allow us to determine the tensor charge of the U and D quark to this kind of precision. This shows the expected precision. And this is very important. And in the interest of time, let me just tell you a little bit about the generalized parton distribution. And the golden process to access such quantity, which is also 3-dimensional distribution function, is through so-called deeply virtual Compton scattering. Now, we are all familiar with Compton scattering. The only difference is here, the initial photon is not a real photon, it's a virtual photon associated with the electron scattering. So such measurement will allow you to access generalized parton distribution, and one particular so-called GPD is very interesting in the sense that if you do calculus first moment, that will tell you the total angular momentum of the quark. And from inclusive DIS measurement, you already know the quark spin contribution, so that will allow you to access directly the orbital angular momentum. And here shows the current knowledge based on Hermes result at DAISY in Germany and Jefferson Lab, Currently, the constraints are not very precise. Nevertheless, that's a major advancement in the field, and this program will continue into 12 GeV. And in the near future, we will have much improved constraint on the total angular momentum contribution of the U quark and D quark to the proton spin. In the remaining time, let me tell you a little bit about how we can use proton as a laboratory to test standard model and look for new physics. So electron scattering, we know, is dominated by one photon exchange diagram. However, we also know that the Z boson exchange is always there. On the other hand, if you try to do a cross-section measurement, you realize right away it's not possible, impossible to see the effect due to the neutral current contribution. However, if I do a parity-violating experiment using polarized electron beam and unpolarized target, I can pick out such an interference term which will amplify the effect due to the Z boson exchange. And this can be used to study proton structure, such as the weak charge of the proton using parity-violating electron scattering. So weak charge here corresponding to the coupling, the charge for the coupling of the protons through Z boson. So that's called weak charge. And in the electromagnetic case, the coupling is to the photon. And we can also do parity-violating electron scattering in the deep elastic kinematics to look for new physics or test standard model. So here shows the Nature paper published a couple years ago or last year about the axial vector coupling to the quark. And the result shows that it is different from the standard model prediction. Of course, the precision needs to be improved. And this brings me to what one can do using 12 GeV, a new instrumentation called SOLID. So this graph I already showed here, which is just a different representation about the current constraint as well as the upcoming constraint with the solid projection here. And then allow me to give you an example how we can use such measurement to constrain new physics. So here again still is the axial vector coupling, as well as we put using the fermion composite model to connect to the new particle scale. And typically, when you look at this kind of contour plot, the smaller the contour is better. But in this case, actually, the bigger is better because we actually can access a new particle or length scale on the order of 10 to minus 20, which corresponding to 15 to 20 TeV scale. And that actually is incredible when you think about you do a parity-violating experiment at 12 GeV, but you are really complementary to what people are doing at LHC in terms of testing standard model and looking for new physics. Okay, so since I no longer have time, let me just come to my summary. And the previous speaker set a very high standard for summary, so the only thing I can match is not to say anything. Thank you very much.
We have time for questions, so if you want to approach the mic for your questions, please do so at this time. You wowed them too much. Now I'm a relativist. Can I ask you a question, sir? Okay, go ahead. Okay.
So you skipped a number of transparencies at the end. And I wonder whether you could say a few words about how an electron-ion collider would actually come into the picture of exploring the proton, as you explained it.
Thank you. So currently, I should say that in the last 2 decades, the entire nuclear physics QCD community has been working very hard, thinking ahead, looking into the future. And the next frontier of QCD, or I should say the tool for us to study QCD frontier is the electron-ion collider. And currently, the long-range planning for nuclear physics is ongoing. And there are 2 proposals to realize such a facility in US. One is at Brookhaven National Lab. The other is at Jefferson Lab. This facility will compare with HERA previously, is high luminosity and polarized beam, both electron, proton, neutron, and helium-3, as well as high luminosity not polarized, but electron nuclear collision at the electron-ion collider, and also will provide a variable center of mass energy. And this is actually important to answer the questions. And I give you a flavor of what's going on in terms of QCD and Nucleon structure, but there will be unanswered question at the end of the day without electron-ion collider, because what we really want to ask in the end is to answer the question about the gluon and C-quark contribution to both the transverse spatial and momentum structure, as well as the gluon contribution to the nucleon spin. And then, of course, there are also very important questions one like to ask about related to nuclear physics, such as gluon density saturation, as well as short-range nucleon-nucleon correlations, and many other important questions. So just to give you one example to highlight what the electron-ion collider will do, I show you about the Rick spin result on the gluon helicity or spin contribution to the proton spin. And here shows with more data what the Rick spin program will accomplish about the proton gluon spin contribution to the proton spin. And with electron-ion collider at this particular center of mass energy, you will see the uncertainty and the knowledge will significantly improve. So this is just give you one example.
This just connecting on to that question. What do you think are the implications for the QCD phase transition? For example, in the early universe, there's also a span of some temperature uncertainty when that happens, and so can you comment on that?
That is a little bit difficult to comment because my focus has been on the so-called cold QCD, which is the nucleon structure. But on the other hand, of course, in the end, globally, it is all connected. Remember what I said earlier in terms of we are currently not able to directly predict the property of the neutron and proton from QCD. So once we understand the nucleon structure from QCD, that certainly will have implication to the question you asked.
Thank you. Any other questions? Then let's thank all three speakers for coming.